Let us now go back to the Jupyter Notebook and see how we can understand what is going to happen now in terms of, first, a code which runs in Cartesian coordinates. Then we're going to write a new code which runs in polar coordinates. So if we look at the first code, we have the standard definitions. We do a final time, which is now 10-dimensional time units. We define a step size in time, which is 10 to the minus 3. We find the number of integration points or mesh points. We define now a two-dimensional array in X and Y with endpoints. So this is actually a matrix. And we do the same for the radius. So this is our two-dimensional radius and two-dimensional velocity. We just define these constants just to make life simple here. We have an omega 0. I also define an angular momentum to 1. So these are just simple choices which I've made. But what I do now is that I go back to the definition of this R min in terms of the angular momentum. And this corresponds now to the minimum value of the potential energy or the effective potential energy. I then define my x0 to be R min. So our x0 now squared plus y0 squared should correspond to R. So the initial condition means that this R min is going to be the kind of radius which I will have for the system. And this is going to span a circular orbit. So I then define my V0 to have a x component, which is actually equal to 0. And then I now calculate my the velocity in the y direction in terms of the square root of this natural frequency times this R min. And that is actually the equation which I need in order to define the velocity. And then I define the arrays for the different quantities with initial values. And then I use the standard methods here, which we have seen many, many times. So this is actually my velocity valet method. And this is now running in Cartesian coordinates. So I have my acceleration, which is simply the radius times the natural frequency of the system. I update my position with the velocity valet method. I need that one to calculate a new acceleration, which I then use to update my velocity. And then when we make the plot here, you will now see that my radius squared has a value which now oscillates around 1 basically, and it takes values which an arrow actually here, which you can see here, which is 10 to the minus 7 plus 1. So my original radius, the way I set it up here, if we now go back to the R min here, I put angular momentum equal to 1, k equal to 1, m equal to 1. So R min is actually equal to 1. And what you see here, due to the choice of a time step, this gives me an error which now oscillates between 1 plus minus 10 to the minus 7. So you see about 10 to the minus 7 here. So the radius is 1. And this is the error I make with a time step of 10 to the minus 3. If I were now to decrease the time step and still keep the same final time and rerun everything, you would then see an error which goes like 10 to the minus 9, which is actually something which we would expect here. And if you now look at the X and the Y position, they are obviously oscillating between 1 and minus 1. And you see the Y position here starts at 0. I started with the X position at 1, and then it goes down to minus 1. And then I have Y, which starts at 0, goes up to a maximum value of 1, goes down to minus 1. And keep in mind that R is actually X squared plus Y squared and the square root of these quantities. So this is a typical kind of situation which we now would have encountered if we had run everything in terms of Cartesian coordinates. And as I mentioned to you in the beginning, if you run the calculation in Cartesian coordinates, you will be able to separate the equations in the X and the Y directions. They will never be coupled, and you can find easily the analytical solution. Now, what you could do next is actually to change the equations so that you would have now a calculation which is set up in terms of polar coordinates. So in our case now, we have to be a little bit more careful. So we need now the value for the radius, which is given in terms of the number of integration points or mesh points. Now this has now been reduced to a one-dimensional problem. In the previous case, we had a two-dimensional problem. Here I just define some constants which I'm going to need when I calculate the potential energies and the accelerations. So my R min is the same as before, that doesn't change, but now I specify R0 to be R min. So I don't need to specify R to have an X and Y component, but it's simply a problem now which has been reduced to a one-dimensional problem since the potential does not depend on the angle phi. Then, when I now run the calculations, I need to simply redefine my acceleration because my acceleration now has an angular momentum term. So we can just paste that in here with an angular momentum term because we have this effective force and effective potential. And that is a term which I have plugged in here. So this is the previous term, which I also had in the Cartesian problem. But then since I'm now making this transformation to polar coordinates, I need now this additional artificial term. Then I update my positions and velocities using the velocity delay algorithm. And in this specific case here, when I'm now setting up the total energy, I have now to include this additional term, which now includes the angular momentum, which is this term which I defined as C2 up here. With that, I can also plot the total energy here and see if that is conserved. So if we do that, you will see now that my radius, which was set up to 1 here. So I started with the radius at R min, which translates into the value of 1 when I look at the parameters which I had. And you see now that the radius stays the same. Now the solution here oscillates much less, and that is simply because we, instead of solving a two-dimensional problem, which we did in Cartesian coordinates with X and Y, we can now simply solve the problem in just one dimension. And that normally gives us a better accuracy of the solution because we have reduced the dimensionality of the problem. Now, when we then look at the energy, we see also that the energy in this particular case is equal to 1 because we made this specific choice of constants. But what we see here is that the energy is conserved as a function of time. And that is what we actually wanted here. But to repeat a little bit, so we can run the problem as we did before in terms of Cartesian coordinates. That means that we need to update X and Y. But we can actually go back to the problem in polar coordinates and simply look at the position as a, or rather the value of R. And then this means that when we fix R at the bottom of the potential, this is going to give us a radial acceleration, which is 0, which means a radial velocity, which is constant. And that means that we are going to have a circular motion. So the radius is actually a constant. And when we now are going to the gravitational force, we are going to see a potential which is a little bit different from this. It's going to have states which we will call bound, but it's also going to allow us to have unbound states. However, the kind of analysis, when we look at the potential at its minimum here, that potential at the minimum value is going to fix a radius, which or a value for the radius r, which corresponds to circular motion. And that's a very interesting result. When we are now going to move away from the minimum, depending on the shape of the potential, we may get elliptical motion, we may get parabolic motion, or we may get hyperbolic motion. And this is what we are going to investigate when we now move into a gravitational force problem, where we actually can solve the equations analytically when we deal with the equations in polar coordinates or spherical coordinates. I leave it as an exercise to you to see if you can actually find the typical input values or the initial conditions which are needed in order to obtain an elliptical motion for the harmonic oscillator. Now we're going to stop here with this specific case. And after we have analyzed this in homework number 8, we are then ready to move into more realistic cases like the gravitational force, or we could actually look at the Coulomb force acting on two charged particles.